Okay, I am continuing with my example problems from chapter 5. This is example 515. All right, so now I am now pulling this crate with some kind of angle. So in example 513, suppose you move the crate by pulling upward on the rope at an angle of 30 degrees above the horizontal. How hard must you pull to keep it moving with constant velocity? Assume that mu k equals 40. So here's our crate. Here's my rope. I'm pulling upward at an angle of 30. And I know mu k equals 0.40. And that's a unitless quantity. Okay, so I've got a tension here, and I'm solving for that tension. I need to know how hard I need to pull. So some of the forces in the x are going to equal to T cos 30 minus Fk equals 0. And I know it equals 0 because I'm pulling it at constant velocity. So therefore, in an inertial state, it has no acceleration. And some of the forces in the y are going to equal to T sine 30 plus my normal force equals my weight, or minus my weight equals 0. This pulling it upward is going to relieve some of that normal force, right? It's going to lighten the load, if you will, right? If you have experience pulling a wagon and you tilt the handle up, it's easier to pull it than if you pull it straight. So I'm interested in my normal force. So my normal force is going to equal to the weight minus T sine 30. And I'll rewrite that equation in T cos 30 equals F of K. Now I know my F of K by definition is going to equal to the normal force times mu K. All right, so I'm going to rewrite all this as T cos 30 equals, the normal force is going to be mu K times weight minus T sine 30. And let me pause and clear up some room for myself here. All right, and oh, a pen. I'm working with these equations. So let me distribute. So here we go, T cos 30 equals mu k w minus mu k T sine 30. All right, I want to solve for T. So T cos 30 plus T sine 30 times mu k is going to equal to mu kw. Pulling out a T, I'll get T cos 30 plus sine 30 mu k equals mu kw. So T is going to equal to mu kw divided by cos 30 plus sine 30 mu k. And once again, I'm going to pause and clear up some space. All right, I believe we were given that W was equal to 500 newtons in that former problem. So now we have mu k. I'll put in my values now. 0.40 times 500 newtons divided by cos 30 plus 0.40 times sine 30. And I'm going to go with their value in the book, and they get T equals, so T is going to equal 188 newtons. All right. Okay, this is example 516. And it reads, let's go back to the toboggan we studied in example 510. The wax is worn off, so there's now a non-zero coefficient of kinetic friction, mu k. The slope has just the right angle to make the toboggan slide with constant velocity. Find this angle in terms of W and UK. All right, we'll take the sum of the forces in the X, right? Sum of the forces in the X equals to that mg, or do they use weight? Weight sine alpha, that's mg sine alpha, minus f of k, and that's going to equal to 0 because it's a constant velocity. Now, some of the forces in the y are going to equal to the normal force minus the weight times cos alpha, and that's also going to equal 0 because it's inertial in that frame of reference. All right, so W sine theta equals N mu K, right? From this guy, I've just redefined that as N mu K. And we have N equal to the weight. This is it there, that's that, times cos alpha. So just by, what am I solving for? I'm find the angle in terms of W and mu K. All right, so let me go ahead and do that. So W sine alpha equals W cos alpha mu K. So let's see, sine alpha I'm going to divide through by cos alpha and W sine alpha over W cos alpha equals mu K. So tangent alpha, these guys go away, equals mu K. So there's the angle in terms of mu K. All right, 517 says the same toboggan with the same coefficient of friction as in example 516 accelerates down a steeper hill. Derive an expression for the acceleration in terms of GA, mu K, and W. All right, so I know what that means. That means I'm going to have an acceleration. So let's see, mg sine alpha, that's my acceleration minus friction, which would be mg cos alpha mu K equals ma. And so, by the way, to explain this, this is the force pushing it down the hill, and this is the force of friction. And they're not it's not an inertial state, so it does have an acceleration right there. All right, so now I just need to derive an expression for A. So I have an m in every term. I can cancel that. So A is going to equal G, I'll pull that out, sine alpha minus cos alpha mu K. And you're done. There you go. All right, 518 is terminal speed of a skydiver. And it reads, for a human body falling through the air in a spread eagle position, the numerical value of the constant D, big D, in equation 5.6 is about 0.25 kilograms per meter. So D equals 0.25 kg per meter. And then it asks us to find the new terminal speed for a 50 kilogram skydiver. Mass equals 50 kg. Okay, and now I'm going to use equation 512. So 512 says V terminal equals the square root of mg over big D So that's going to be equal to the square root of 50 kilograms times 9.8 meters per second squared divided by 0.25 kilograms per meter. Okay, and let's see. That's going to give us 44 meters per second. 518. 519 is a force in uniform circular motion. All right, and it says a sled with mass 25 kilograms. Okay, rests on a horizontal sheet of essentially frictionless ice. It is attached by a 5-meter rope, 5.00 meter rope. I'm assuming that's R. To a post set on the ice. Once given a push, the sled revolves uniformly in a circle around the post. If the sled makes 5 complete revolutions every minute, 5 RPM, find the force F exerted by it on the rope. All right, I need to know the velocity. So I'm going to do 5 times R is 2 pi. R is times 5.0 meters. That's 5 revolutions. That's the distance. Per minute is 60 seconds. So I need to know that speed. Let's get that. I think your book does it differently. Skips a step, but I'm not going to do that. 5 times 2 times pi times 5 equals, divided by 60 equals 2.6 meters per second. So now my force centripetal is equal to mv squared over r. That's going to be equal to 25.0 kgs times 2.6 meters per second quantity squared. And r is 5 meters, 5.0 meters. All right, so let's square that. And m is 25 kgs times 25 equals, divided by 5 equals. And let's see, e squared over r. Something went wrong here. I'm not getting the same value. Wait a minute. Oh, that's terminal speed of a skydiver. Yes, I am getting the same value. So my bad. I was looking at the wrong problem because I got 34.2 meters per second squared. So that is the answer to 519, 34.2 meters per second squared. You can do it like I do. You can do it the way the book did it. Is, you know, there's a lot of ways to solve these problems. All right, I'm on number 520. And let's see. 520 says that an inventor, it's a conical pendulum. It says an inventor decides a pendulum clock using a bob with mass M at the end of a thin wire L. Instead of swinging back and forth, the bob is to move in a horizontal circle at constant speed V, with the wire making a fixed angle beta with the vertical direction. So we've got this mass M. This is R. This is beta, and remember it's with respect to the vertical, so we're going to have to change our X and Y thinking, and this is L. Okay, so now we are to find the tension in the wire and the period T. All right, so there's some force here, so the sum of the forces in the X are going to be equal to, call that F sine beta, and that's going to be equal to M acentripetal. And the sum of the forces in the y are going to be equal to F cos beta minus mg equals 0. All right. And let's see, I've got to solve for the centripetal. So I'm going to get something for F here. I'm going to use this guy. I want to, when I want to substitute it, I want to have a tangent. So you'll see why I do that. F cos beta equals mg. F is going to equal to mg over cos beta. And now we go back here to this guy. So we have a mg times sine beta over cos beta equals m acentripetal. And so I don't need these m's. So I'm going to come out with acentripetal equals tan beta. All right. I'm going to pause, clean up my board, and continue. All right. Now I am supposed to solve for the period. And they use this equation, a centripetal equals 4 pi squared r over t squared, where t is the period. That's what we want to solve for. And we'll go ahead and use that. And if you want to know the derivation for this, you can just check in the instructional videos, chapter 5, I believe. And there's a nice derivation for this, or you can just take it on faith if you'd like. So we were solving for t squared. T squared equals 4 pi r divided by tan beta. I'm just go ahead and substitute tan beta for there. And I could just simplify one more time by recognizing that r equals L sine beta. So I'm going to go here and I'm going to say this is, oh, this is squared, sorry. 4 pi squared L sine beta over sine beta over cos beta. And I'm going to get, oh, that's t squared, isn't it? So let me erase just a skosh right here. So now t squared equals 4 pi squared. And these sine betas are going to go L cos beta. Oh, I forgot a g. Where was my g? There was a g here, right? Over g, sorry. Over g. And then taking the square root of both sides just to solve for t. And I'm going to get t, if you will. Oh, let me erase a little bit to clear this up. T is going to equal 2 pi square root of L cos beta over g. And we're done. 521 is rounding a flat curve. Rounding a flat curve. And it states the sports car in example 311 is rounding a flat unbanked curve with radius r. If the coefficient of static friction between the tires and the road is mu s, so we've got mu s, what is the maximum speed Vmax at which the driver can take the curve without sliding? All right, so here we go. We've got the sum of the forces in the x. And remember, it's flat. So we know that if it's not going to slide, the friction's got to equal that centripetal force. So F equals m a centripetal equals m v squared over r. And the sum of the forces in the y is equal to the normal force minus mg equals 0. So now I'm going to work with this. Okay, so I know the friction force by definition equals N mu K in this case, right? And that's going to equal to m v squared over r. And we're flat, so n is going to equal mg. So we're going to have, this is going to be mg mu k equals mv squared over r. I don't need these m's. What am I solving for here? V max. Okay, so V max is going to equal to G R mu, this is V squared max, mu K, and take the square root of both sides, and V max is going to equal to the square root of G R, this is mu K, sorry, mu K, and that's 521. 522 states that for a car traveling at a certain speed, it's possible to bank a curve at just the right angle so that no friction is needed to maintain the car's turning radius. Then a car can safely round the curve even on wet ice. Bobsled racing depends on this. Your engineering firm plans to rebuild the curve in example 521 so that a car moving at a chosen speed v can safely make the turn even with no friction. At what angle beta should the curve be banked? Okay, so let's do this. We've got that. We've got the vertical. We've got R here. And we're going to bank this guy here. This guy, I guess that's the curve right here, this beta, and that will be this angle. Right? It's going to beta. All right, and just to show you if my angle is beta here, I've got this right angle and I've got this right angle, and so this has got to be 90 minus beta. So this is going to be beta as well. All right, this is the normal. And if you can see, it's got a horizontal. Remember, this angle is with respect to the vertical. So the horizontal component, f of x, equals n sine beta equals ma. And f of y equals n cos beta and then that's going to be minus mg equals 0. So n cos beta is this guy minus mg, that's going to equal 0. And n sine beta equals n ma. Oh, and this is acentripetal, by the way. And I'm going to divide these equations by each other. So I'm going to have n sine beta divided by n cos beta equals m acentripetal divided by mg. So now tangent beta is going to equal to acentripetal over g. Am I done? Oh, I just have to expand the acentripetal. So let's see. What am I solving for here? B. Okay, so tangent beta equals v squared over rg, or gr as they have it. And so now my beta is going to equal to tan inverse of v squared over gr. Okay. Do I have values there? No, I don't. I'm leaving it there. Wait. I guess they didn't give me values, so we'll leave it at that. All right, 523 is uniform circular motion in a vertical circle. And it says a passenger on a carnival Ferris wheel moves in a vertical circle with radius r and a constant speed v. The seat remains upright during the motion. Find expressions for the force the seat exerts on the passenger when at the top of the circle and when at the bottom of the circle. All right, so the centripetal force is always going to go towards the center of the circle, and that's how you solve this guy. So the force y at the top is going to equal to the normal at the top, is going to equal to the minus mg, right, equals negative mv squared over r. So we're solving for the normal at the top. The normal at the top equals mg minus mv squared over r. And let's see, they took out a 1, but let's just do m equals g minus v squared over. All right, that's at the top. At the bottom, well, let me pause and clean up the screen. At the bottom, oops. At the bottom, we have the normal at the bottom minus mg equals mv squared over r. That's going upward. So we have the normal at the bottom equals mg plus mv squared over r. So that's going to equal to m times g plus v squared over r. And there you go. I think that's the last problem in this chapter.